Of all the moons in the solar system, ours is truly unique. It's the only one large enough and close enough to stabilize its mother planet, Earth. But our moon is spinning away, and at an increasing rate. And eventually, it will be too far away to stabilize Earth. Take away the moon, and Earth topples over, causing catastrophes worldwide. Extreme temperatures vaporize water and melt ice. Oceans could rise hundreds of feet. And massive dust storms and hurricanes rage for generations. Without our moon's protection, life as we know it will perish from the Earth. If the moon travels just 10% farther from where it resides today, 25,000 more miles or so, we'll reach a point of no return. That's when the Earth's rotation becomes chaotic, unpredictable, and unable to sustain nearly all forms of life. Scientists know the moon is retreating because they have monitored its movement for the past 40 years.
Neil, yes, we are getting a TV picture.
In 1969, Apollo astronauts leave the first of 3 suitcase-sized boxes embedded with reflectors. NASA's visionary idea is that one day we'll be able to use lasers to measure the moon's distance with more precision. They were right. And this is the tool they use today, the Apache Point Observatory Lunar Laser Ranging Operation near White Sands, New Mexico. Dubbed Apollo for short, it uses those reflectors to calculate the moon's distance down to the width of a human fingernail. But measuring how fast and far the moon is receding is difficult. Here's how it works. First, the laser pinpoints a moving target from a moving source, 250,000 miles away, through distortion caused by Earth's atmosphere.
We have a laser mounted on the telescope. The laser light travels out to the moon, where it encounters retroreflectors left behind by the Apollo astronauts. So it's a special kind of mirror which reflects the light directly back where it came from. Those reflectors send the light straight back to our telescope, and it comes back to our detector. We can measure the timing of the light traveling to the moon and back with extreme accuracy, and that allows us to measure the distance to an accuracy sometimes as little as 1 millimeter.
The advantage of a laser beam is that it travels long distances very quickly. The round-trip distance to the moon is 500,000 miles. So it takes light about 2.7 seconds to make the trip. But the Apache Point laser has its risks.
This is going to be our interlock control system. If any of certain safety conditions are not met, it will close a shutter so that the laser can't shine.
Aircraft are the biggest concern. So scientists alert air traffic control to keep planes out of the airspace.
It would not permanently damage anyone's eyesight. It would probably affect a pilot's night vision, which would be undesirable, so we try to avoid that.
On this night, the moon is mostly dark during its crescent phase. Using a guide camera to help aim the laser, Dr. McMillan locates a visible feature on the moon whose distance from the reflector is already known. From there, she'll know exactly where the reflectors are hidden in the darkness.
This is a crater called Pierce. It's way over here on the corner of the moon here, over here on the illuminated side of the moon. And then we'll go to Apollo 15 reflector, which is in the dark portion of the moon.
Tonight's sky looks clear to the naked eye, but the upper atmosphere is blurring the instrument.
Right now it's not looking very good. It causes the laser beam to expand. It expands it, fuzzes it out on the way up towards the moon as it passes through Earth's atmosphere, and also on the way back down, coming back from the moon to our detector. So we get hit twice by that kind of shaky behavior from Earth's atmosphere.
With the laser aligned, it's now or never.
Okay, cross fingers. Okay, coming out.
The Apache Point lunar laser beam reaches the moon in less than 2 seconds.
If you were standing on the moon, you would see a bright pinpoint light. It would be pure green light.
This laser light is saturated with photons to ensure it bounces back.
The laser is strong enough that even though only about 1 in a quadrillion of the photons that we send out comes back and gets detected, because we're sending out many quadrillion photons, we're detecting a pretty fair number.
It's a bit like throwing a pile of sand at a mini trampoline 250,000 miles away and hoping a few grains bounce back. The more grains you throw, the better your chances.
Here's the outgoing signal being detected by our internal detectors. We would like the incoming signal to appear here. And there it is. It's a beautiful big spike. It looks perfect.
Decades of continuous measurements have shown that the moon is moving away from the Earth at a rate of about 1.5 inches per year. That might seem like a tiny distance, but over time, it adds up.
Sometimes we take for granted how important this moon is to our pure existence here on this planet. Well, you've got gravitational pull from the moon onto the Earth, and so the moon is very tightly coupled to what's going on the Earth.
Our moon has the largest mass in the solar system in relation to its mother planet. And size matters. The large mass helps stabilize Earth. Gravity is the key to their relationship. It's the force that draws objects together. In space, it works a bit like balls rolling toward each other on a blanket. Gravity's strength depends on the size and distance of those objects. So the closer and larger the mass of the objects, the greater the attraction. And since the moon is the largest, closest body to Earth, the gravity between them is powerful. From 250,000 miles away, the moon's gravity holds our planet steady on its axis.
And this is very important because we have a very stable axis at about 23.5 degrees. Earth rotates around its axis once per day.
That smooth, even 23.5 degrees enables sunlight to spread widely across the planet, maintaining the Earth within a relatively narrow range of temperatures, a range proven ideal for life.
We have a very nice, very stable climate system here based on the tilt of our axis staying the same. And so this is very key because we need to have this stable situation for life to be able to take hold and then evolve and survive and thrive and be in the situation we're in now.
That stable axis also creates our regular seasons as it orbits the sun. When the North Pole tilts toward the sun, that angle creates a temperate summer in the northern hemisphere and winter in the southern hemisphere. And when the North Pole is tilted away, the opposite is also true. It creates winter in the northern hemisphere and summer in the southern. It's the moon's stabilization of Earth that maintains the sun rising in the east and setting in the west.
And if we had the Earth not in this nice stable axis thanks to our moon, you would see sunrises and sunsets happening at different times in different places in the year.
Without the moon's gravity, regular and predictable seasons would not have occurred, and plants and animals would not have evolved. Take the moon away today, flowers wouldn't bloom, and bees no longer pollinate in spring. Geese would no longer fly south for the winter or north in the summer to breed, and seeds would no longer drop from trees in the fall to germinate. Even with the moon's stability, the Earth still has a small periodic wobble of 1.5 degrees on its axis. This is the natural result of gravity exerted on Earth by other, larger passing planets. As the moon continues moving away, the Earth will be thrown further off its axis, causing an even greater wobble. And larger wobbles can have big consequences for humans. Roughly 100,000 years ago, just a minor wobble changed the angle of the sun's rays on Earth enough to turn lush forests into the Sahara Desert. An event that likely forced some of the first humans to migrate north out of Africa. Further north, from Europe to North America, the wobble prompted an ice age lasting thousands of years.
So even events such as the ice ages and things that we think of as major events on the Earth, think about how much more dramatic those would be if we didn't have this moon here.
The Earth would become unrecognizable. Climates would become unpredictable. Temperatures would vacillate wildly. So the moon's impact on Earth is critical. Its gravity even affects our tides. Astronomer Tom Murphy explains.
We have this polar view, the North Pole here, here's North America.
These blue particles represent the Earth's daily ocean tides.
The moon is off to the right, far off the screen.
The particles bulge directly toward and away from the moon.
If you're sitting in North America, you experience a low tide, and then a high tide, and then a low tide again, 12 hours later after the first low tide, and then a high tide.